So the first example that we went through in the class is we are moving a charged body of 3 coulomb from A to B, where the work done in moving it from A to B was given to be 18 joules. So you know that work done moving a body from A to B is VB minus VA by there's a test charge, but here it's not a test charge, it's 3 coulomb of charge. So work done itself is 18 by 3, so it's 6 joules. They've given that the point A is at a minus 2 volt of a potential. What is the potential at B? What is the potential at B? So then therefore 6 is equal to VB minus of minus 2. So VB plus 2 is equal to 6, and VB is equal to 4 volts. This is sum which we saw in the class. Therefore, you should know that this formula WAB by Q naught, or it can even be Q, will be VB minus WAB is VB minus VA. So the next question, here in an order, the new volume, I have example 1, which is given in the potential. Find the electric potential surface of an atom of nucleus which has got radius 9.0 into 10 to the power minus 13 centimeter. So it's 9.0 into 10 to the power minus 15 meter. And atomic number is given to be Z is 50, which means this many protons is there. So they ask you for the potential on the surface. The potential on the surface and inside is all the same. You know that. So V is equal to 1 by 4 pi epsilon naught into Q by R. But Q is not Q, it's Q is N into E, which is n is 50 into E. So 9 into 10 to the power 9 into 50 into charge of a proton is 1.6 into 10 to the power minus 19 by the radius, which is 9.0 into 10 to the power minus 15. So then this will give you the potential at that point. Just calculate it. Okay, you have to get answer as 8 into 10 to the power 6 volts. 8 into 10 to the power 6 volts should be the answer. Let's go to the next question. The seventh question, calculate the potential at a point P due to a charge 4 into 10 to the power minus 7 coulomb located 9 centimeter, which is 9 into 10 to the power minus 2 meters away from this. So it's just 1 by 4 pi epsilon naught into Q, which is a source charge, by R, which is the distance. Just do the calculation. This itself is 9 into 10 to the power 9. So just do the calculation. You get the potential at that point, which will be 4 into 10 to the power 4 volts. The next part of the question is find the work done in bringing a charge of 2 into 10 to the power minus 9 coulomb from infinity to this point P. If you're going to bring it from infinity, you know the potential at the point P, which you found out to be 4 into 10 to the power 4 volts. The potential multiplied by the charge that you're going to bring will give you the work done. P is equal to W by Q, W is equal to V into Q. So then that's about it. This answer would turn out to be 8 into 10 to the power minus 5 joules. That's your example 7. And that's the example 2. Does it depend on paths? Does the answer depend on the path along which it's brought? No. You know, potential energy does not depend on the path because it only depends on initial position and the final position. Even while we are doing potential, we calculate the R8 and RB. Remember, we integrated from RA to RB, and all that is required is initial position and the final position. The final formula obtained will be the work done in bringing it from is VB minus VA. So the 1 by 4 pi epsilon naught into Q by RB minus 1 by 4 pi epsilon naught Q by RA shows that it only depends on initial and final position, does not depend on the path taken. That's what happens with the conservative force. And so then this is the work done, which is also because of the conservative nature. So let's go to which depends only on the initial and final position. A metal wire is bent in the form of a circle of radius 10 centimeter, 10 into 10 to the power minus 2 meter, which has got a charge on the surface 200 microcoulomb, which spreads uniformly on the surface. Okay, calculate the electric potential at the center. If the electric potential on the surface will be the same as electric potential at the center, I told you E is equal to minus dV by dr. Since the electric field inside the cavity is zero, the potential should have been a constant because differentiation of only a constant can be zero. Therefore, this whole thing is the same potential. So just calculate the potential of the surface 1 by 4 pi epsilon to Q by R. 9 into 10 to the power 9 and 200 into 10 to the power minus 6 by R is 10 into 10 to the power minus 2, and then substitute this value, get the voltage on the surface, which is same as voltage inside also. Don't follow what Aurora has done. It's complicated. It's just that what is on the surface is what will be inside in the case of potential. So it's called equipotential surface. Let's go to fourth example. The electric field intensity at a point B to a point charge Q kept at A. Electric field intensity at a point B. Okay, it's been given that it's 24 Newton per coulomb is the electric field, and the potential at that point is also given 12 joule per coulomb. This is electric field and this is V, and moment, E is equal to V by D is the way the mantra, D is equal to V by E. So it's 12 by 24, 1 by 2, which is 0.5 meters. Thus you get this distance to be 0.5 meter. Once you know the distance, they're asking you for the charge. That's the enclosed charge. Potential's formula. So V is equal to 1 by 4 pi epsilon naught into Q by R, where R itself is 0.5 meter. Potential itself is 12 joules. This itself is 9 into 10 to the power 9. Just substitute everything. 12 is equal to 9 into 10 to the power 9 into Q by 0.5. You can cross multiply, get the value of charge. Thus, you can find the charge enclosed that happens to be 0.667 into 10 to the power minus 9 coulomb. Okay, that will be the answer. You can calculate it for yourself. Let's go to the fifth question. To what potential we must charge an insulated sphere of radius 14 centimeter, 14 into 10 to the power 14 into 10 to the power minus 2 meter. To what potential should we charge it so that the surface charge density is charge per surface area 4 pi r square itself is 1 microcoulomb per meter square, which is 1 into 10 to the power minus 6 is equal to Q by 4 pi r square. You know what is R? Is 14 into 10 to the power minus 2 the whole square. With this, you can cross multiply, get the value of charge. So thus you find what is the charge then, and what are they asking? They're asking for the potential on the surface. Potential. Once you know the charge, is 1 by 4 pi epsilon naught into that Q by this R. So once you get the charge from cross multiplying, substitute it here and get the potential. So you get the answer to be actually 15840 volts. Just check your answer if it's correct. Let's go to example 6. A charge of 24 microcoulomb is given to a hollow metallic sphere. 24 microcoulomb is given to a hollow metallic sphere of radius 0.2 meter. Find the potential at the surface of the sphere. Okay, charge of microcoulomb. Yeah, it's 1 by 4 pi epsilon naught into Q by R. Q, R. This micro means 10 to the power minus 6. Just get the value. You get the potential to be 1.08 into 10 to the power 6 volts is the answer. Now find the potential at a distance 0.1 meter from the center. It's a equipotential surface. What is it? The surface should be out is inside. So inside also is the same answer. So let's go to example 7. There are 27 droplets. Okay, each one at a potential of 220 volts. 220 volts. And the radius of this is, let's keep it a small r. And 27 such droplets, 27 into 4 by 3 pi small r cube, is coalescing to form a bigger droplet 4 by 3 pi capital R cube. 4 by 3, 4 by 3 pi get cancelled. 3r is equal to capital R. And the potential for smaller droplet, which is 220 volts, is equal to 9 into 10 to the power 9. That's 1 by 4 pi epsilon naught into Q by R. You don't know Q by R itself. You don't know Q, you don't know R. Let's find Q by R's ratio using this. So 220 by 9 into 10 to the power 9. So you calculate this value, get a Q by R ratio, and the question is find the potential on the bigger droplet. 1 by 4 pi epsilon to Q by capital R. But Q is not Q because 27 droplets would have coalesced. So one droplet's charge is Q, it's 27 into Q. So it's V is equal to 9 into 10 to the power 9 into this R, capital R is nothing but 3R because we have a relationship here. This is 9Q by R. What is R here? Small r. And you know what is Q by R itself. Just bring this value here, substitute. You should get the potential to be 1980 volts. So let's go to example 8. two small conducting spheres of this is of sphere A and this is of sphere B, each one of radius r1 and r2, having charges q1 and q2 already, and after which you're connecting a conducting wire, which means the charges is going to flow from higher potential lower potential, thereby acquiring new charge, which is q1 dash and q2 dash, which will be responsible for the potential. And so the potential will be equal in after the charges are flowing. And so then 1 by 4 pi epsilon naught into q1 dash by r1 should be equal to 1 by 4 pi epsilon naught into q2 dash by r2. So then therefore q1 dash by q2 dash is equal to r1 by r2, and that's what happens here. And then that the charges are conserved. That is charge q1 plus q2, which was initial, should be equal to q1 dash plus q2 dash after it's flown, should be equal to the total charge capital Q. Just mark this as your equation. Then cross multiply this q1 dash into r2 is equal to q2 dash into r1, and instead of q2 dash you can substitute capital Q minus q1 dash. So capital Q minus q1 dash into r1 is equal to q1 dash into r2. Okay, now you can take it in and multiply. You get q a small r1 minus q1 dash into r1 is q1 dash into r2. Consolidating the q1 dash, you can consolidate the q1 and q1 dash. You get r1 plus r2 is equal to qr1. So q1 dash therefore is qr1 by r1 plus r2. Q itself is q1 plus q2. You can also substitute q, it's q1 plus q2, which is the initial charge, into r1 by r1 plus r2. Now they're asking for q2 dash. Q2 dash is capital Q minus q1 dash. Capital Q is the total charge minus q1 dash we just found out. Let's substitute it in the here, which is, let's substitute q r1 by r1 plus r2. And when you substitute that and you take LCM, you get r1 plus r2, a qr1 plus qr2 minus qr1, qr1 get cancelled. Thus you're getting a qr2 by r1 plus r2, where q itself, q1 plus q2, which is initial, into r2 by r1 plus r2. So thus you get q1 dash and q2 dash. You can even keep it as q only. This is also fine. And if they ask you the ratio between q1 dash by q2 dash, it's qr1 by r1 plus r2 by qr2 by r1 plus r2. So it will still be r1 by r2, which is the same as what we got previously. There's no change. It's still the new charges, and it's the same ratio as the radii. So let's go to the next question, which is the ninth question. In the exam, the test paper, I asked you ratios of the surface charge density. If you remember, it was q1 by 4 pi r1 square by q2 by 4 pi r2 square. In that, the q1 and q2 were the charges after connecting itself. So surface charge densities ratio, there you got q1 by q2 into r2 square by r1 square. Since you know q1 by q2 itself is r1 by r2, you'll get answer to be r2 by r1. Okay, by equating both the voltages, a very very important sum. Let's go to ninth question. So then there is a 3 into 10 to the power minus 8 coulomb and a minus 2 into 10 to the power minus 8 coulomb, which is 15 centimeter watt, 15 to 10 to the power minus 2 meter. At what point of the line journey the potential can be zero? Nowhere between positive and negative charge electric field can be zero. So where can the electric field be zero? It can be zero to the right side of a smaller charge. Okay, forget about it. This question is about potential. The potential is possible for it to be zero in somewhere in between and also here. So then in this case, you'll assume this is x and this is 0.15 minus x. So you write the potential due to this charge, which is 1 by 4 pi epsilon naught into 3 into 10 to the power minus 8 by x, plus 1 by 4 pi epsilon naught into, due to this charge, is minus 2 into 10 to the power minus 8 by 0.15 minus x, should be equal to 0. The net potential is 0, taking the middle part. So then therefore this is equal to this. This gets cancelled. 10 to the power minus 8 get cancelled. The 2 minus 2 and goes, that's it, becomes a plus. So 2 by 0.15 minus x So on cross multiplying, you get 0.45 minus 3x is equal to 2x. So 5x is equal to 0.45. So x is equal to 0.9. And 9 5 are 45. So then x is equal to 0.9. The other part will be obviously 0.6. But you also know the other extreme, on the complete other extreme, you can have the potential to be zero on the right side of a lesser charge. So you have to continue with that. Mm, So as I told you, even the other extreme, because this is 3 into 10 to the power minus 8 coulomb, and this point in here is minus 2 into 10 to the power minus 8 coulomb, where the distance of separation, is 0.15 centimeters, and you can also have the potential here also to be 0. In that case, I'll assume the whole thing as x. So this will be x minus 0.15, and so the potential due to this charge will be 1 by 4 pi epsilon naught into 3 into 10 to the power minus 8 by the whole distance, which is x, plus 1 by 4 pi epsilon naught into this charge is minus 2 into 10 to the power minus 8. In potential, you have to take negative as negatives, positive as positive, it's not vectors. So by x minus 0.15 is equal to 0. So this and this get cancelled again, this and this get cancelled. Taking the other side, 3 by x is equal to 2 by x minus 0.15. So 3x is equal to 3x minus 0.45 is equal to 2x. So x is equal to 0.45. Can you see that it can even be far away from both the charges on the right side, the potential can be 0. So thus you find this value. The next sum is about calculate the electric potential at the center of the square. At the center of the square of side root 2 meter. Each side is root 2 meter, root 2 meter, root 2 meter, root 2 meter. Okay, at the center. So what about the charges? There's a 100 microcoulomb. There is a minus 50 microcoulomb. There is a 20 microcoulomb. And there's a minus 60 microcoulomb. And first of all, we need to find the potential at the center. You need to know what is this distance. If this is root 2, side is root 2 and root 2. Okay, so it will be root of root 2 square, which is 2, plus root 2 square, which is another 2. So root 4 is 2. And the entire diagonal is 2, and half of it will be just 1. Therefore, this distance is just 1 meter. Okay, so then due to this charge, what is the potential? 1 by 4 pi epsilon naught into minus 50 into 10 to the power minus 6 by 1 meter, plus due to this charge is 1 by 4 pi epsilon naught into 100 into 10 to the power minus 6 by 1 meter, plus due to this charge it's 1 by 4 pi epsilon naught into minus 60 into 10 to the power minus 6 by 1 meter, by due to this one is plus 1 by 4 pi epsilon naught into 20 into 10 to the power minus 6 by 1 meter. Just add all this. It's negatives and negatives you can consolidate, positives and positives you can add, and so you can find the net answer. So this is how we find the potential at the center. Okay, so then I hope you understood. Let's go find the answer. It has to be 9 into 10 to the power 4 volts should be the final answer. So let's go to example 11. Where plus the question is you have okay, let's not do example 11. Let's go to some of the sum. The sum that I did in the class is I think I did the 14th question. I did the 14th question where two charges minus q and plus q are located at a point 0 comma 0 comma minus a, which means it's on minus a, which means the negative z axis. 0 comma 0 comma minus a is in the negative z axis. The point A is here and the point B is at 0 comma 0 comma a. Okay, so this is on z axis. How much work is done in moving a discharge from 7 comma 0 comma 0, which means on the x axis 7 comma 0 comma 0 to minus 3 comma 0 comma 0. So we are moving it along the x axis and this is along the z axis. And can you see that a minus q and a plus q, which is like a dipole? So the dipole is along z axis and you're moving a charge on the along the x axis, which is like an equatorial line. So the work done will be 0. So because the potential on equatorial line is 0 for a dipole, for a dipole which is along the z axis, the x axis will be perpendicular to it. And so moving a charged particle on an equatorial line will be 0. So that is one sum that I want to tell you. Next is I also did these sums where they had asked for the total potential energy. Is an example 27. Example 27, there are four charges at the corners, okay, such as the four charges at the corners of squares ABCD. Find the work done to put them together. So it has got a plus q. This has got a minus q. And this is example 27. You should also try the other sums, but I'm doing only the important ones here. You must also try the other sums. And so then what is the work done to put this arrangement together? So then the side of the square is given to be d. Every side is d. Okay, so you take this potential energy, which is 1 by 4 pi epsilon naught into minus q into plus q. So minus q square by d. This potential energy 1 by 4 pi epsilon naught into q into minus q is minus q square by d, plus this 2 is 1 by 4 pi epsilon naught into minus q square by d again, plus again between this and this is 1 by 4 pi epsilon naught into minus q square, because q into q potential energy involves multiplying both the charges by the d. So then it's potential into charge, it's work done, it's nothing but potential energy. So this, plus apart from this we have to take the diagonals. It's 1 by 4 pi epsilon naught into q square by, if it's d and d, what will be the diagonal? Diagonal will be root of root 2 into d. Okay, so then therefore it's root 2d plus 1 by 4 pi epsilon naught into this diagonal, which is 1 by 4 pi epsilon naught into q square. Because anyway, the negative also will become positive here because it's squaring, multiplication of minus q, and this minus q is plus q square. And so q square by root 2d. Just solve this, you should get the answer. You should get the net potential energy, whose answer should be minus q square by 4 pi epsilon naught into 4 minus root 2 should be the answer. Just check this answer if you're getting it. Okay, that will be the net potential. A net work done in putting the system together. So many joules. So what is the question can also be, what is the work necessary to be done to take this charges to infinity? That will be this is negative, that will be plus q square by 4 pi epsilon naught into 4 minus root 2 joules, because amount of work done necessary to put them together will be equal in magnitude to the amount of work that's necessary to be done to be taken to infinity, but only opposite symbol, positive work and negative work, that's the only thing. Okay, so now thus you find the potential. Thus you know this is the energy. Now charge q naught is brought to the center e. Oh, so you're again bringing another charge to center E of the square. The four charges being held in fixed corners. How much extra work is needed to be done? Um, so you know that the again how to find you, if you know the potential on the at this point at the center. If you know the potential at the center, have we done the potential at the center by any chance? I just did the work done to put everything together. But when you consider this to be at the center, you should know that the potential becomes zero. The last sum we had, in this sum, we had some potential at the center. But because they were all different charges, but here they're all uniform charges, plus q minus q plus q. So one is positive and the other is negative, and this distance will be root 2d by 2, which will be d by root 2 in that case, this half the distance. So you write 1 by 4 pi epsilon naught into this charge is minus q by the distance is d by root 2, and this distance, what is it? It's 1 by 4 pi epsilon naught into q by d by root 2 with a positive sign, but this is with a negative sign, and then this is with a positive sign. So when you write all those values, everything will get cancelled. The net potential at the center will become zero. So the work done bringing any charge from infinity to that point at the center will be zero. So let's continue with the next sum. The next sum that I did in the class is this, where they have given a plus q, a plus 2q, and a minus 3q at vertices present at ABC. You're going to bring this point charge to A dash, A to A dash, B to B dash, and C to C dash. So, what is the work done in moving it from initial position to final position? What you should do is this is the example 28. You find the initial potential energy minus final potential energy. Initial potential energy is between this, and between this. 1 by 4 pi epsilon naught into this charge into that charge by distance. If this distance is given to be L, then this blue color will obviously be L by 2. L by 2, L by 2, L by 2. So it's the same charge which is getting shifted, but the distance is different. So you can write for the initial is in purple color. It's 1 by 4 pi epsilon naught into Q into 2Q by L plus 1 by 4 pi epsilon naught into 2Q into minus 3Q by L plus 1 by 4 pi epsilon to Q into minus 3Q by L. That will be the initial potential energy. What will be the final potential energy? Let me write in blue color. 1 by 4 pi epsilon to same charge only. The distance is all L by 2. So 1 by 4 pi epsilon naught into 2Q into minus 3Q into L by 2 plus 1 by 4 pi epsilon naught into Q into minus 3Q by L by 2. So then there'll be a 2, 2, 2 up. Everything else will be same. So you just have to take it out and find the difference between the initial potential energy and the final potential energy. Just calculate it, and when you subtract, you were supposed to get U final minus U initial will turn out to be 1 by 4 pi epsilon naught with a negative sign 7q square by L. Just calculate this value and subtract the purple minus, I mean blue color minus the purple color, you'll get the answer. So there are much more sums which are there, but I didn't do those sums in the class. I expected you to do it at home and come back and ask me for doubts. Okay, so this is what I took in the class on potential.